Welcome to the video course on VLSI design. In this lecture, we are going to discuss the preview of MOS transistor followed by MOS transistor theory. First, let us commence with the preview of MOS transistor. In order to understand the MOS transistor, one should understand the working principle of diode or PN junction. So, what is a diode? A diode is basically a electronic device, electronic component which is formed by connecting p-type and n-type semiconductor materials, specifically silicon materials. The semiconductor diode has a p-type region which is also called as anode, and the n-type region which is also called as a cathode. Now, how to apply voltage to the PN junction? There are two ways the PN junction diode can be biased. Number one is forward bias. When the anode voltage is higher than the cathode, then the diode is said to be forward biased, and this allows the current to flow. Alternatively, the diode can be biased in reverse mode. When the anode voltage is equal to or lower than the cathode, the diode is said to be reverse biased, and during reverse bias only the minimum current flows through the device. This is about PN junction or diode. Now let us have a look at transistors. The transistors can be broadly classified into two types, which is bipolar junction transistor, shortly we call as BJT, and the second transistor is metal oxide semiconductor field effect transistor, shortly we can call this as MOSFET or MOSFET. Now, let us go through the working principle structure of MOSFET, and in this lecture, we are not going to discuss bipolar junction transistor. Already in the previous class, we have discussed the history and the working principle of bipolar junction transistor. The reason why we are moving to the discussion on metal oxide semiconductor field effect transistor is because today's electronic systems or electronic applications uses MOSFET as a basic element. Nearly 99.99% of our electronic system is made up of the MOSFET compared to the BJT. Of course, the bipolar junction transistor has very good property such as switching speed is good in BJT. However, there are plenty of advantages of MOSFET over the BJT. The MOSFET takes little power to control the current movement between one terminal to the other terminal, and also the fabrication is very easy using MOSFET as compared to the bipolar junction transistor. The meaning is the MOSFET can be fabricated easily in the integrated circuits compared to the bipolar junction transistor. With that background, let's move on to the discussion of MOSFET structure or MOS structure. The metal oxide semiconductor structure is made by layering conducting and insulating materials, which is structured in a manner that resembles sandwich-like structure. Okay, so the sandwich-like structure contains different material. In the same way, the MOS structure also contains different materials, namely the conducting and insulating materials. The structure is produced by chemical processing techniques. So the various chemical processing techniques are as follows. Oxidation technique, which is oxidation of silicon, which we call as SiO2, that forms an insulating layer. Selective doping, that introduces impurities, acceptor or donor impurities. Acceptor impurities create a P type of the MOSFETs. Donor impurity create N type of MOSFETs. And this method, adding impurities to the pure semiconductor to increase the conductivity, is called as doping. Now, the third step is deposition of metal wires. In order to connect the component to other components, other devices, we need to deposit the metal wires. Generally, in MOSFET, the metal wires is made from the polysilicon, also called as polycrystalline silicon, which acts like a metal. This is a polysilicon is a silicon that is made that is converted into the metal. Okay, this works like a metal similar to the copper or aluminum, and this enables the electrical connections, which we can make easy connections to the other components. And the fourth step is the etching process. that refines and patterns the structures. So these are the four chemical processing techniques that is widely used in manufacturing or making the metal oxide semiconductor field effect transistor. Okay. The MOSFET works on the principle of field effect. So in these words, you can see that MOS describes the structure of a MOSFET. M stands for metal, O is oxide, S stands for silicon, metal oxide silicon or metal oxide semiconductor. The last three letters indicates the working principle, field effect transistor. That means the MOS FET works on the principle of field effect. So what do you mean by field effect? That is we are going to discuss in the upcoming the classes. Here, the field is mainly established in both directions, vertical and horizontal directions. So these are the electric fields created by different voltage that we apply to the MOSFET. So two types of fields, namely vertical and horizontal field, are responsible to make this device to conduct and use in variety of applications. Namely, the switches and amplifiers are the main applications of the MOSFETs. In general, the transistors. The transistors or MOSFETs have heavily doped N plus regions. So N indicates normal doping, and when we show N as N plus, that shows it is an heavily doped. Okay. So this is heavily. This meaning is heavily doped. And at P plus, similarly, the P is normal doping, and P plus indicates it is heavily doped. So these are the two heavily doped regions that you can find in NMOS and PMOS respectively. Okay. So mainly the N plus and P plus regions are used to increase the electrical properties and also to improve the performance of the MOSFET. And here I'm going to show you a small clip from the YouTube that illustrates the working principle of the MOSFET. Just a moment. So let us go through the
Uber or
working principle of the
fare
MOSFET
starting from
with the help
rupees
of this
49.
small clip.
Uber. Let's go.
I have to finish this paper. I'm swamped. No one told me college would be so damn.
So with this, we have understood the working principle of MOSFET. Now let's continue our lecture. So now next let us look into the transistor manufacturing process, how transistors are manufactured. Transistors are built on single crystal silicon wafers that are highly pure and nearly defect free. Okay, there should not be any defect material on the silicon, so that the transistor is completely is defect free. So now let us see the type of wafers what we use. The wafers serves as a foundation for the integrated circuits. Typically, the diameter of the wafer is 15 to 30 centimeter, and which serves as the base for the modern semiconductor devices. Here is a picture of the how silicon wafers are produced. This is nothing but a silicon ingot, where you can see the a cylindrical type of material here. That is a large bulk silicon, and this is cut into the small slices, which you are seeing here using the diamond blades, and these small slices are called as wafers. And here is a detailed picture of a silicon wafer where ICs are integrated circuits are fabricated. Okay, so this is about silicon ingot and the wafer. Next, let us move to the CMOS technology. As we know that CMOS stands for complementary metal oxide semiconductor. It's a technology that integrates both N-channel metal oxide semiconductor field effect transistor and P-channel metal oxide semiconductor field effect transistor. So the one and only technology that combines both NMOS and PMOS is the CMOS technology. So we see everywhere the CMOS transistors, especially in the modern era, where in the integrated circuits you see only the CMOS transistors instead of NMOS or PMOS alone. So these CMOS transistor performs switching action, and also logic functions can be derived from those CMOS transistors along with amplifier applications as well. Now let us move to the scaling of transistors and design automation. As we have seen in today's scenario, the transistors on a chip has grown exponentially. We have discussed in the previous class about Moore's law. As per the Moore's law statement, the number of transistors doubles every year. Okay, that is the statement of the Moore's law. And again, the productivity also keeps increasing because of the advanced in the automation tools. And we should appreciate the contribution for that is going to be the hardware description languages. Shortly, we call this as HDLs. Mainly, HDLs can be classified as VHDL and Verilog. These are the popular hardware description language where we can write Verilog, statements that describes the hardware, and through that we can develop, we can fabricate the integrated circuits. We can automate the integrated circuits from the Verilog and VHDL code that enable designers to define circuit functions. We can easily explain the working principle of the circuit using either the VHDL and Verilog. VHDL is popular in academics, and whereas Verilog is widely used in industry. And using these languages doesn't need to manage individual transistors. Without that, we can automate the circuits using these two languages. Despite of automation, also we need to understand the fundamentals of circuit design, because to handle the complex design, the basics of circuit design plays a key role. So now let us look at the CMOS layout and its fabrication. Just like that basic transistor fabrication, CMOS transistor fabrication also needs special attention. The CMOS transistors are generally it is mass produced using a technique called as lithographic process. The process that is incorporated in making a CMOS is a lithographic process, which is almost similar to the printing press. Okay, so layout design involves the following, the regions which we define the following regions in the layout. First of all, the dopants are diffused into the silicon substrate that forms, N type or P type, the type of semiconductors. Then polysilicon is grown to form the transistor gates. The polysilicon serves as a transistor gate. Next, the metal layers is deposited in order to establish the electrical connections. And finally, the contacts are etched to interconnect the different layers of the transistor. So these are the steps, and here we have shown the inverter schematic circuits. So here we have an upper transistor is the PMOS transistor, and the bottom one is going to be the NMOS transistor. This is a CMOS circuit wherein which we have both PMOS and NMOS transistor. This is the schematic of inverter circuit, and this schematic can be a layout can be developed for this schematic here. Here is the layout of a CMOS inverter, which contains the P diffusion followed by N diffusion, then the pink color layer here that shows the polysilicon that serves as a gate material, and we attach the a metal. Here we have a more number of metal pieces. This small rectangular portion forms a metal, and we can see that here the PMOS, to decrease the resistance, we have added more number of metals here. And NMOS, and by default it has got very low resistance, and we have only few metal layers here, a metal layer here, and there is a metal layer here that decreases the resistance of the NMOS. So combining together PMOS and NMOS, we have taken the drain points, that serves as the output, and here we have clubbed both gates, the polysilicon interconnected, that forms the input. So this is the layout of a CMOS inverter. Next, the VLSI design and microprocessor implementation. The CMOS design has been extended even to implement the microprocessors, because in microprocessor, each CMOS transistor will be modeled as a switch. Basically, in a microprocessor, each switch or CMOS transistor works like a switching device, and basically it is used as a logic design to make the CMOS circuits. Using this CMOS logic gates and latches can be developed also, because this is an extension of the gates, CMOS logic gates. That is a basic components of the CMOS. This logic gates, if it is combined, the connected properly, that can be extended even to the switches. So this chapter, what we are discussing right now, covers all the principles required to do the design of the logic circuits, and also teaches us a layout of a basic CMOS chip. A key example is the design of the 8-bit MIPS processor. MIPS stands for million instruction per second processor, a high-speed microprocessor, which is an 8-bit, which introduces a key challenges in the digital circuit design. And one thing what we recommend for the students is this subject is basically of learning by doing. It is the best approach in order to master the VLSI design. So it is a practical approach that teaches us how to be mastering the VLSI design. The laboratory exercises are available in the following link www.cmosvlsi.com. That is a link provided by the authors of the main textbook, prescribed textbook, and that can help in designing of a microprocessor chip. Next is the importance of the MOS technology in modern electronics. We all know that MOS transistor is used widely in most of the electronic systems. It is essential for the digital logic circuits and also the microprocessors. The MOSFET MOS technology enable high-speed operation, which you don't see in the bipolar junction transistor. MOSFET is also known for low power consumption, the ultra low power consumption that we can see in the CMOS especially, and also the device miniaturization, shrinking of device. It's quite possible through the MOS technology, which is very difficult in case of the bipolar technology. The advances in MOS technology have driven continuous improvements in, especially in the computing power and even the efficiency. The state of the art technology as of now is going to be the CMOS technology. So with that, we have given a preview of the MOS transistor. Now let us have a look at the details of the MOS transistors. So MOS we already specified. MOS stands for metal oxide silicon or semiconductor transistors. Here we introduced the silicon first to begin with in order to understand the MOS transistor. Silicon, the name for this is the symbol for this is Si, is the main material used for making the integrated circuits because silicon is the second abundantly available material on the Earth's crust. This you can see how exactly the silicon is available, that is shown in the first photograph. And we have taken a photograph from the Wikipedia that shows how exactly the silicon material extracted from the Earth's crust appears to be. So silicon is as it was mentioned, it is the second most abundantly available element on the Earth's crust, and it's a semiconductor. Of course, it has got four valence electrons in the outermost orbit, and it has electrical properties which lies between the conductor and an insulator. And now let us look at the atomic structure of the silicon. Silicon is an atom. It's a material that has got 14 electrons. In the outermost orbit, we can see that there are four electrons. So therefore, this all semiconductors in general are going to be the tetravalent. That means outermost orbit has got four valence electrons, and electrons here, the outermost electrons forms the bonding. This is called as a covalent bond that forms bond with adjacent atoms by sharing equal number of electrons with the adjacent atom. Example is this silicon atom shares one electron, this also shares one electron, and that forms the a bond, equal sharing of electrons. That such kind of bonding is called as a covalent bonding. If you observe the practical, the bonding, the shape of the silicon structure is going to be the tetrahedral shape. This follows a diamond pattern that is shown here. This is the practical, the structure of the silicon. And now let us look at the from the periodic table perspective, where exactly silicon lies and what group it belongs, and how to increase the conductivity of silicon, as we'll discuss it with the help of the periodic table. When we look at the periodic table, it's again categorized into the groups and the periods. Row wise, what we see is going to be the periods, and column wise, what we observe here, the elements are going to be called as a groups. And the silicon actually it falls into the group 4 element silicon, and even germanium, as we can see here, this carbon, silicon, germanium. Okay, so many semiconductors, all this falls into the fourth group in the periodic table. And prior to that, we can see that group 3 elements are there. So these group 3 elements basically added to the pure semiconductors in order to increase the conductivity. Not only group 3, but also we add group 5 elements to the group 4 elements in order to increase the conductivity. That is illustrated in the following sections. Group 3 element example is going to be the boron, one best example, and even aluminium. And the group 5 elements are going to be, the popular one is going to be the phosphorus and arsenic. These are the elements that we dope with the group 4, which is a pure semiconductor, in order to increase the conductivity. So silicon atoms form three-dimensional structure, lattice structure, that we already discussed here. This is the lattice structure of the silicon. and silicon is a group 4 element in the periodic table, meaning that each silicon atom can form the four covalent bonds with its neighboring atom that we have already discussed. And here is the structure, stable crystal structure, or also known as cubical crystal structure, which has formed with adjacent atoms. You can see that this is a silicon atom and this adjacent neighboring silicon atom. We have illustrated here, the totally 9 silicon atoms that forms, a, a type of bonding by equal sharing of electron. It forms a covalent bond with the adjacent silicon atoms. This line indicates it is a covalent bond, okay, with when which equal sharing of electrons will take place from one silicon atom to the adjacent silicon atoms. Now let us have a look at conductivity of the pure silicon. Pure silicon is basically a poor conductor of electricity because of the following reasons. Because all valence electrons are involved in the covalent bond, as we have seen already. There is no electron left vacant, okay, leaving no free electrons to carry the electric current. There are no electrons available to carry the electric current. Therefore, the pure silicon is going to be, it works like, it's a poor conductor. Okay, so how to increase the conductivity of the pure silicon? The material here, as we have seen, pure silicon does not easily allow the movement of charge carriers. If, by using a methodology to increase the, to adding, the some impurity elements, if by any chance we can increase the free carriers, electrons or holes, then the conductivity can be increased. We'll see that here in the next section, how to increase the conductivity of the pure silicon. To increase the conductivity of the pure silicon, small amount of impurities, also called as dopants, are added to the silicon. Okay, we'll see that how these dopants are added to the pure silicon, and adding this, dopant elements, that increases the conductivity of the pure silicon. Dopants are nothing but they are the elements that change electrical properties of silicon by adding, the free charge carriers. Okay, so how to add, the doping elements, we'll see that here. So let us first start with an n-type semiconductor. The n-type semiconductor, also called as negative charge carriers, and or the electron-based charge carriers, are present in the n-type semiconductor. So to increase the conductivity of the pure silicon, let us consider the group 5 elements of a periodic table. The group 5 elements are arsenic and phosphorus. These are the two elements that are preferred over other dopants. Why group 5? The reason for selecting the group 5 is because these elements have 5 valence electrons in the outermost orbit, whereas silicon has got only 4 valence electrons in the outermost orbit. Now here, adding the 5 valence electrons to the silicon atom, adding the group 5 elements to the silicon, creates one extra electron. Okay, so that is illustrated here. When a group 5 atom replaces silicon atom in the lattice, it is still bonds with 4 neighboring silicon atoms, leaving one extra or fifth electron vacant. It doesn't have a place to form the covalent bond, and that is left vacant. This, extra electron or free electron, what we call, is, because is due to the reason of the adding the group 5 element. For every impurity element that is added, impurity atom that is added, we get one extra electron. So that means the number of impurity atoms increases, corresponding the number of electrons also increases. Now let us see how this increases the conductivity. The extra electron is now loosely bound to the dopant atom. It is not tightly bound to the parent or adjacent or neighboring atom. A small amount of thermal energy, especially at room temperature, can free this electron without attaching to any atom. This electron can be made free, and it's available to move anywhere. Okay, that's why the name is called free electron. This movement of free electrons, which will allow the current to flow from one point to the other point, making the entire material as a conductive. Okay, this is how the conductivity of pure semiconductor can be increased by adding group 5 elements to the pure silicon. So in this process, the n-type elements, we get n-type of semiconductor, means n stands for negative type of semiconductor. Reason is the entire the silicon is now flooded with the free electrons, and these free electrons carry the negative charge. This is evident from the figure 1.7b. Let us show the figure 1.7b. Here you can see here. So these are the silicon atoms. Earlier we have seen the pure silicon atom, silicon, the structure, and here, the silicon with added impurity, the group 5 element has been added here, and as we can see here now, all this, silicon arsenic forms, the bond with this adjacent silicon atom, and also with this, and as well as this and this. But again, the one electron which is left out here, that free electron can be easily removed at room temperature. Even with small amount of thermal energy, that electron can be detached from this neighboring, from this arsenic, impurity element, and that becomes free. Okay, so this is how the one can create, the n-type, semiconductor. Now let us have a look at p-type semiconductor. The p-type semiconductor, also called as a positive charge carriers or holes, because p-type semiconductor creates enormous amount of holes. To create this p-type semiconductor, now we need to consider group 3 elements. The example for group 3 elements are boron and gallium. Any impurities can be considered here. These are used as a dopants. Why group 3 again here? So as we have seen in group 5, the group 3 elements have 3 valence electrons in the outermost orbit, whereas silicon has got 4 electrons in the outermost orbit. When a group 3 atom replaces a silicon atom in the lattice, it can only form 3 covalent bonds, leaving one missing electron, and that is nothing but the hole. The absence of electron or missing electron is called as a hole. That means the group 3 impurity added creates a hole in the semiconductor, in the pure silicon. So how this hole increases the conductivity. Now the missing electron creates a hole which behaves like a positive charge carrier, and the neighboring silicon atom now donates, start filling that, filling an electron to the that particular hole, and it creates a new hole in another position here. And this process continues, and holes keeps moving, hole keeps moving, and making the entire material as a conductive. And this process creates, the p type of, the semiconductor. P means it is a positive type of semiconductor, and moving holes act as a positive charge carriers movement, and this can be seen from the figure 1.c. In figure 1.c here, it is clear that we have added boron impurity element here, and this forms a covalent bond with the 3 neighboring silicon atoms, and one side where we can see the absence of electron, that is considered as a positive hole. And this hole, to fill this hole, now the adjacent electrons may be, the moving here to fill this hole, and that creates again another vacant position here. These are how the p-type semiconductors are made. So we understood now p-type, n-type and p-type semiconductors. Now let us have a comparison between the n-type and p-type semiconductors. And here let us use, various properties to compare the n-type and p-type semiconductors. The property type is dopants. In n-type semiconductor, the dopants are group 5 elements. Example is arsenic and or phosphorus. Whereas in p-type semiconductor, we are supposed to use group 3 elements. Example is boron or gallium. The extra or missing electrons. Extra electron is the fifth electron, fifth valence electron, which is an additional electron that is formed by adding the impurity element. Whereas in case of p-type semiconductor, there is a missing of electron that forms the hole. The charge carriers in n-type semiconductors are the free electrons that we show with minus sign, whereas in p-type semiconductor, the holes are the majority charge carriers. The charge carrier type is negative in case of n-type semiconductor because of due to the electrons, whereas in p-type semiconductors, the charge carrier type is going to be the positive, and due to the holes, enormous amount of holes present here. The conductivity mechanism in case of n-type semiconductors is electrons that move freely within the semiconductor, whereas in case of p-type semiconductor, holes move by borrowing electrons from the adjacent or neighboring atoms. The property wise, if you look at here, this is a n-type semiconductor, and the p-type semiconductor is by group 3 elements, and n-type semiconductor is by group 5 elements. Now we have seen the importance of the n-type and p-type semiconductor. Now let us see the importance of semiconductor doping. Doped silicon is used to create essential electronic components such as transistor, diodes, and microchips. These are the elements that can be created by using a doping method. The combination of n-type and p-type materials that forms, the p-n junction, that is the foundation for majority of the modern electronic devices. Semiconductors control electricity flow, making them essential for all the electronic devices. Now let us move to the understanding of the p-n junction. Though we already discussed diode or p-n junction, which is nothing but obtained by, the combining p-type and n-type semiconductor. The p-type region acts like an anode, n-type region acts like a cathode, and we already discussed about forward bias and reverse bias. Anode voltage, if it is higher than the cathode voltage, that is forward bias. This has got, all this allows the current to flow from, okay, the electron to flow from N to the P, and current to flow from P to the N. Whereas reverse bias, the anode voltage is equal to or lower than the cathode voltage. The diode is reverse biased here. This will only causes the leakage current to flow within the device. So understanding of, the diode is very important in order to understand the MOSFET. This is the structure of, the diode. This is a diode symbol, and the anode is P type is called as an anode, and N type is called as a cathode. This is the structure of a PN junction or a diode. Now let us look at the structure of a transistor. The transistor is now to make a transistor. We start with the P type of substrate, and this is called also as a bulk. This bulk is of, silicon type. The entire metal is silicon here, and now we diffuse with N plus, which is heavily doped N plus regions. Two N plus regions you can see, which are, the doped into the P type substrate, and we attach terminals to the this, and in between these two regions, N plus and N plus region, we deposit, silicon dioxide. The blue color here, that shows the silicon dioxide. On top of that, we deposit the polysilicon, which acts like a metal. So polysilicon is nothing but a metal layer. Now you can see that the why the name is MOS. This is a metal, and there's a silicon dioxide, which is SiO2, and there's a semiconductor. That's why the name is called metal oxide semiconductor, metal oxide silicon. Okay. Now we attach terminals to this each of these regions. For the N plus region, here we attach a source terminal, and for the another N plus we attach a terminal which we are calling as a drain terminal. And to control the charge carrier movement from the source to drain, we have here the third terminal called as a gate terminal. Gate acts like a control terminal. And same thing we can see even in the PMOS or P channel device. In the P channel device, we start with the N type of bulk or N type of substrate, and we diffuse with the P type P plus regions, two P plus regions that serves as a source and drain regions respectively. Uh, combining these two regions, we have a intermediate, which is again silicon dioxide, and the top layer serves as a metal, which is the polysilicon. Now the symbolic representation of the MOSFET is as follows. This is a symbol of a MOSFET. So we have I'll write a bigger version of it. This is the N MOSFET. We don't have anything here. This is the structure here. So we have a gate here. We have a source and a drain here. This is the drain region, and this is going to be the source region. And here we have channel formation region, and the top layer is nothing but it is the metal, and there's a space between the metal and the semiconductor. That space indicates it is silicon dioxide SiO2 region, and we attach the gate to the metal, gate terminal to the metal. So this is a symbolic representation of the NMOS transistor. Another symbol for the symbol for the PMOS transistor as same as NMOS, but here we'll have a bubble here saying that lower voltage here will turn on this PMOS device. So the PMOS symbol is here, and this is going to be the NMOS symbolic representation. As usual, here again this P region here serves as a source and drain. That is here, this region is nothing but a source region, and here this line shows it is a drain region. And once again the gap here indicates it is silicon dioxide, which is an insulator, and there is a metal here this thick line here shown, it is a metal layer, and there's a bubble shows that it is a PMOS transistor. So often we use these symbols to write the circuit, to develop circuits of various the NMOS and the PMOS based circuits. So we use these kind of symbols because drawing the cross section or drawing the dimension like this becomes very hard to show the circuits. So each transistor here stacked structure, as we have seen here, it has got a conducting gate which acts like a control terminal. It has got insulating layer which is made up of silicon dioxide, commonly known as a glass. A silicon wafer, which is a bottom portion, which is nothing but substrate or body or bulk. We can call it different names. Let us look at the evolution of MOS technology. So MOS technology, early transistor uses metal gates, especially from aluminum or using aluminum or copper. Okay, but the metal oxide semiconductor present day uses polysilicon as the metal layer. Since 1970, the gates have been made from polycrystalline silicon, but the term MOS remains even now as same. In 2007, the metal gates re-emerged again to address material challenges in advanced semiconductor manufacturing. Now let us discuss on the NMOS transistors. In NMOS transistors, already we explained that. This is once again reiterating here. The NMOS transistors are built from the P type of body or P type substrate, and N type regions are adjacent to the gate known as the source or source and drain. The body is typically grounded. As we can see, the body or bottom portion is typically grounded. The source and drain are physically equivalent and can be regarded as interchangeable. The one difficulty in MOSFET is the source and drain. These two terminals can be interchanged. Okay, so these two terminals can be interchanged because of equal doping across the source region and the drain region. Same thing can be done even for the PMOS as well. Okay, that is about the NMOS transistor. PMOS transistor, again, it has got the P-type source and drain regions, and body or bulk is of N-type, and this works exactly opposite to that of the NMOS transistor. Now let us see the CMOS technology. CMOS technology uses both NMOS and PMOS. It's a combination of both NMOS technology and NMOS transistor and PMOS transistors. The substrate in the CMOS circuits is either N-type or P-type, depending on the type of transistor. Okay, so to integrate both NMOS and PMOS transistor, the opposite type of transistor must be built within a special well. The well is basically created by adding dopant atoms to form the body of the opposite type. This is very important in while making CMOS, because CMOS houses both NMOS and PMOS transistors. So look at NMOS transistor. That the NMOS transistor gate will act like a control input that allows the regulate the current flow from the source and drain region. Generally, the NMOS transistor body is grounded, body or bulk it is kept at the ground potential, and PN junction between the source and or drain and the body are reverse biased, preventing the current flow. When we don't apply any voltage, the diode created between the source or drain and the body, that remains as a reverse biased, and that prevents the current flow. If gate is also grounded, then there will be no current flow within the transistor, and we say that transistor is in off state. And when the gate voltage is increases, as we increase the gate voltage, electric field is generated acting free electrons to the in the Si and SiO2 interface, and that causes the current to flow. Okay, let us go through the diagram and illustrate this operation what we are trying to explain here. So this is let us consider the NMOS transistor here. NMOS transistor here. So if you apply here the voltage, which is of the a positive voltage similar to this voltage I am going to call as VGS, because it's a voltage applied between the gate and source. Now let us see this how this works. So the positive voltage is applied to the metal. So this upper metal layer is now provided with positive charges, and here this is a substrate or bulk region is of the P type. The majority charge carriers in this is going to be the holes. However, the minority charge carriers are the electrons. These positive charges in the upper plate above silicon dioxide now can attract electrons, which are minority charge carriers in the bulk region. And when this voltage is increased, what happens is all the electrons which are minority charge carriers in the bulk region or substrate region, they occupy this silicon dioxide interface. You will see a lot of electrons here accumulating because of the large positive charges in the upper plate. And now this creates this region is called as a channel that creates a path for the electron to move from source region to the drain region. Now we have created a path between the source and drain by applying the gate source voltage. Now for these electrons to move from source region to the drain region, we need to apply a voltage, another voltage called as drain source voltage. So let us call this as drain source voltage. So this is VDS, drain source voltage. So with reference to the source, the drain voltage is applied. Now we can see that here the positive terminal of a battery here attracts the electron here to the positive terminal here. So the electrons now are creating the holes here that is filled by the electrons here, and so you can see the electron movement from source to drain in this way, and that is attracted to the positive terminal of a battery, and again electrons are supplied by the negative terminal of a battery. In this way a path is created. Now current movement between the source and drain is regulated by the gate voltage or gate to source voltage. That's how the NMOS transistor works. The exactly opposite is the PMOS transistor. Whatever the voltage we applied here, that must be reversed here. That's how the PMOS transistor works. Okay, so this is about NMOS transistor. Okay, so as we have said here, the free electrons will be generated in the SiO2 interface. When the high voltage is high enough, the electrons outnumber holes from the thin inverted region under the gate known as a channel. I showed you how exactly channel formation takes place because of the capacitance effect, and this channel help us to create a path between the source and drain. The path between source and drain is called as a channel, and this channel has been created because of the inversion region formed in the SiO2 interface. The inverted channel behaves like a n-type semiconductor because it's filled with negative charges, and that creates a conducting path between the source and drain. Now let us have a look at PMOS transistor. Okay, here in the NMOS transistor current will flow now, and we say that transistor is on. Now PMOS transistor operation is almost opposite to the NMOS transistor operation. The PMOS transistor operates opposite to the NMOS transistor, and body is held at a positive voltage here in this case. Okay, and now if the gate voltage is positive, the source and drain junctions are reverse biased and preventing the current flow. We say the transistor is off. The gate voltage is lowered, positive charges holes accumulate beneath the SiO2 interface, and a sufficiently low gate voltage causes inversion in the channel, creating a conducting path for positive carriers between the source and drain. Now current flows, and now we say the transistor is on. Let's go back to the device and explain that operation. So let us have a look at the PMOS transistor now. So this is the PMOS transistor structure, cross-sectional view. Now let us apply the gate voltage. Unlike the NMOS transistor, we need to apply the uh, positive volt. Sorry. Look at the type of voltage what we're applying now here. So negative should be at the gate and positive should be at the source. This is positive and negative. And now this voltage is we are calling as VGS because it's a voltage applied between the gate and source. Now this voltage, negative voltage is supplied to the metal plate here. Now metal is filled with negative charges. Unlike in NMOS, it is filled with positive charges because we applied positive voltage to the gate. Here we apply negative voltage to the gate. Now this negative voltage attracts the minority charge carriers in the bulk region. What are the minority charge carriers in the bulk region? Of course, it is going to be the positive charges. So positive charges are attracted below the Si, this is silicon and SiO2 interface. As we can see that as VGS increases, more and more positive charges accumulate between the source and drain regions below the SiO2 interface. This is SiO2 interface, silicon and silicon dioxide interface. Okay, so now we can see that now. So this creates a path between the source and drain, and this is called as inversion layer or channel. Inversion layer, it is called as a channel. Okay, because this complete layer it is made up of n type, and because of the voltage that we applied has inverted this n type to p type here, So this forms, this layer is called as an inversion layer, or also called as a channel. Now we apply, if we apply the voltage between the drain and source, now see what happens now here. Okay, so here I must apply the other voltage. Let's see now. You can see the holes here are attracted to the negative terminal of a battery, and the scarcity of holes now is filled up by the from the source region, and again there is a supply of holes from this. So the current flow is like this through the source, through the channel, along with the drain. The holes reaches this. So this is the direction of current flow in the P type of transistor. So that's the way the PMOS transistor works. And symbolic representation already we have discussed. The first symbol indicates the PMOS transistor symbol. There's a bubble here, and there's a source region, drain region, and the empty space here indicates silicon dioxide. Similarly, for the NMOS transistor, we have a source region, drain region, and SiO2 here. The empty space between these two lines indicates it is a silicon dioxide. Okay, now let's move to the voltage notations in the digital with reference to the digital circuit application. The positive voltage is also called as VDD, or we name it as a power that represents a logic 1. A low voltage is also called as a ground, or GND for short notation, or VSS that represents a logic 0. And because of the miniaturization, the scaling of voltage has been has been done since from 1970 to 1980 and even today. The VDD is typically 5 volts in our earlier days, but due to the miniaturization of transistor and modern devices operate at very low voltages, and voltage has been scaled down from 1982 till date with the following ways: 3.3 volts, and we were using 2.5, 1.8, 1.5, 1.2. Present state of the art is not even 1 volt, it is lower than the 1 volt. That's how the voltage has been scaled over the years. MOS transistor also works like a switch, because in today's computer there are we fabricate the billions of transistors. Each of those transistors in the modern digital computer will work like a switch. The gate of the MOS transistor will act like a current will control, and that controls the current flow from the source to drain region. And NMOS transistor, it is on, means it is conducting whenever the gate is 1 or high voltage. And NMOS transistor is off, that means it is not conducting when the gate voltage is going to be 0 or low voltage. And let's have a look at the PMOS transistor. PMOS transistor is on, which is conducting when the gate voltage is going to be 0 or low voltage. For low voltage, PMOS will conduct. And when we say PMOS transistor is off or not conducting, whenever we apply high voltage to the gate, when the gate is equal to 1 or gate has got high voltage, then we say that PMOS transistor is off. That means NMOS transistor likes positive voltage or high voltage at the gate. PMOS transistor always likes has need to have the low voltage at the gate. That makes the device to conduct. Okay, now let us go to the circuit representations. The switch behavior of MOS transistor is represented using the symbols. Uh, we use small g for gate, small s for source, and then small d for drain. The switch model is commonly used to understand the design of circuit behavior. Let us see here how exactly switch behavior can be understood. So this is the MOSFET symbol, NMOS symbol. As we can see here, we have a gate, source, and drain. And whenever we apply gate as 0 or low voltage, that means the transistor is equivalent to the half switch, and in the switch representation we can show it as an open switch. There is no current flow from drain to source, or charge carrier movement from source to drain, that is removed because of gate is equal to 0. When we make gate as high voltage or gate as 1, now you can see the same switch now turns on because G is equal to 1. Okay, so now current flows from drain to source. That means through this particular device, NMOS device, we can make the current to flow 0, and we can make the current to flow maximum by just with the help of the gate terminal here. And let's have a look at the PMOS transistor. Again, the PMOS transistor, we have a bubble symbol, that is a special in case of a PMOS transistor. And here, let us see how this works like a on switch or off switch. Here, when we make when we apply gate voltage as 0 volts, or gate as the zero, the transistor turns on. The on is shown with a closed switch. Here, switch is closed. Okay, so closed switch will allow the current from drain to source. Maximum current will flow from drain to source. However, when the gate is applied with large voltage, the PMOS turns off. When the PMOS turns off, it is shown as a open switch, and when the switch is open, there is no current flow from the drain to source. So zero current. Okay, so this is zero current here. Current here. Maximum current here flows from source to drain. Whereas here in the NMOS case, there is a zero current here and maximum current here. So with the help of this, the understanding, it is clear that NMOS conducts for high voltage, PMOS conducts for low voltage, and interestingly, the CMOS technology uses both NMOS and the PMOS, and because of the NMOS and PMOS, the power consumption or power dissipation in the CMOS is negligibly very small. So with this, we have come to an end of this transistor theory. In the next class, we will explain the CMOS logic styles and how to build CMOS circuits. Thank you and all.